So we are going to start with lattice energy, which is yeah, that was what was left. Born-Haber cycles are basically about calculating lattice energy. So we're going to first discuss what this thing is. Okay, now lattice energy is basically the I mean, this is what the reaction is, that if you have gaseous ions, like you got Na+1 in gaseous state and you got Cl-1, which is in gaseous state. So together they're going to form, if they get together, they're going to form NaCl, which is going to be a solid. So it's about forming 1 mole of solid ionic lattice, and you form it from its gaseous ions. Now the product has to be 1 mole, and it's always going to be energy released. So it's always exo. Why? Because ionic bonds are getting formed. So for example, initially you've got a bunch of and the ionic lattice kind of looks like this. Okay, this is how ionic lattices look like. 1 second. Picture लगा लेते हैं. अच्छा, so here's your typical ionic lattice. So there are gaseous ions flying around and they form an ionic bond, they get attracted to each other, and that's your ionic lattice. Okay, so the definition for this, you clear? Is this part clear?
Yep.
So the formal definition is that it's the energy that is released when 1 mole of solid ionic lattice is formed. Ionic lattice gets formed from what? From its constituent gaseous ions measured under standard conditions. Now, about lattice energy, it's also written as delta HLE, simply lattice energy. Now, the other thing is that if a stronger lattice is formed, that's going to be more exothermic. So, lattice energy, stronger bonds getting formed, it's going to be more exothermic. For stronger lattices. So, when you think is an ionic lattice strong, like what are the factors that determine the strength of the ionic lattice?
Is it how highly charged the ion is?
So it's basically it depends on the charge density. which is what? Which is basically proportional to the charge on the ion. The greater the charge, the stronger the lattice. And it's inversely proportional to the size of the ion or the ionic. Bigger the ion, the weaker the lattice, right? So basically, if you sum this up, it's smaller ions having greater charge are going to form the strongest lattice. So they form stronger lattices. Is this part clear?
Yep.
Now about ions, so you should have some idea about how the ionic radiuses change. So for example, so this is just a brief example on finding out which one is bigger and which one is smaller. So how to determine the relative size of ions? So for example, if I have oxygen, which is 2 minus, I've got neon, and I've got magnesium, which is 2 plus. Magnesium is 12, neon is 10, proton number, and oxygen is 8. Which one do you think is the smallest ion? And which one is the biggest ion?
Is O2 minus the smallest one?
And why?
Because it has the lowest amount of electrons.
So they're actually isoelectronic. They all have exactly the same electrons.
Oh yeah.
So all have 10 electrons. So now tell me which one is the strongest, which one is the weakest, which one is the biggest and smallest. So you look at the protons because the electronic configuration is exactly the same. So Mg has the most protons. Hence, it is going to be the smallest. Is that clear?
Why does that make it the smallest?
Because it's got 12 protons. 12 protons will attract the 10 electrons that are around it strongly. So, I mean, they all have 10 electrons, right? Mg
Yeah.
has the most attractive power out of all those. Is this
Okay.
clear?
Yep.
And oxygen is the least. It's got 10 electrons as well, but oxygen is the least. It's attracting the electrons the least. So the oxygen atom has the biggest, has the least protons. Hence, it's the biggest. It's going to have the least attraction. So that's one thing. So that's how you determine the relative size of ions. So if I tell you, like, if you're going to compare, tell me which of these, who's got the stronger lattice? If I have NaCl versus MgCl2, who's got the strongest lattice?
Is it MgCl2?
And why?
Because Mg has a higher charge, so 2 plus, whereas Na and Cl have 1 plus and 1 minus.
So greater charge, and it's also got the smaller cationic radius. Like Mg2 plus and Na plus 1, right? They both have the same number of electrons. Both of them have how many electrons they've got? They've got 10 electrons. But Mg having more protons is going to be smaller in size. Is this clear?
Yep.
Now, similarly, let's talk about NaCl versus KCl. So basically, the first one, this one is going to have the more exothermic lattice energy. So what about the other one? NaCl versus
Is it
concept?
is it KCl? KCl?
It's got the stronger lattice, right?
Yeah,
Why?
because it has this smaller radius.
No, it's got the bigger radius. So they both have the same charge. Charge is the same, but it's Na. Na has got the smaller radius. Na. In this case, it's Na. But why is it Na?
Is it because it has 11 protons, whereas the other one has 19?
It's got an extra shell. You're moving down the group, right? So I'll over here. I'm going to add that when you move down the group, the ionic radius increases. So down the group, you got more shells. So you get bigger ionic radii, and so Na has the smaller radius, so greater, or you can say more exothermic lattice energy. Is this clear?
Yeah.
So lattice energy, it's the energy that is released when you have 1 mole of solid ionic lattice getting formed from its constituent elements. And the elements are the ions, the gaseous, not the elements, sorry, 1 mole of ionic lattice is formed from its gaseous ions. So if I write the equation for, so what's delta HLE of Al2O3? So if I want to write that equation, it's going to be 1 mole of aluminum oxide getting formed and solid from what? From its constituent gaseous ions, which are what? Aluminium and 3 plus, and oxygen being 2 minus. Is this clear?
Yep.
So now next, the final thing. The final thing is your Born-Haber cycle. Like, what is the Born-Haber cycle?
For that equation, does it need to be balanced? Or is it just going to say it that way?
It has to be balanced. This has to be 1 mole. So there's going to be 3 O2 minus and 2 Al3 plus ions. Is that clear?
Yep.
So now the Born-Haber cycle. The Born-Haber cycle is basically used for calculating lattice energy, because you can't calculate lattice energy directly, because it's very hard to actually form gaseous ions, right? So, and then to turn those gaseous ions into ionic lattice, so it's always found indirectly by looking at the other energy values. Now, Born-Haber cycle, that's uh, so the I mean, you could actually calculate anything, but usually used for calculating lattice energy. And this is how the Born-Haber cycle is constructed. It's that usually you've got an energy axis, and this, so endothermic goes up, exothermic goes down. Now you've got you're going to have different values for example, let's say aluminum oxide. So what you're going to do is you're going to start off with enthalpy change of formation. I don't actually know what the enthalpy change of formation of aluminum oxide is. Just one second. If I can get a value. So that's fairly exothermic. Enthalpy of formation of aluminum oxide. Yeah. So, anyways, enthalpy of formation is what? It's elements. So aluminum solid plus oxygen, which is gas, and together they're forming aluminum oxide, which is exothermic. So the arrow goes downwards. So I'm going to make an arrow, and that arrow is heading downwards. So that's my starting point. That's my enthalpy change of formation. Now remember, formation and lattice energy are different. Like in formation, you've got elements. In lattice energy, you actually make the lattice from its ions. Okay, is this clear? The first part.
Yeah.
So you know the Hess cycle, right? One path being equal to the other path, right? So that's the. I mean, I'll write down the Hess law, which is that the Born-Haber cycle is basically the Hess law, which was what? That enthalpy change is basically independent of the path taken. You're going to get the same enthalpy change no matter what. So no matter what happens in the middle, you're going to get the same thing. So anyways, you've got this part, that enthalpy of formation. Now what we're going to do is we're going to break this into steps. So we're at this point. So how do you, starting from elements, how do you make an ionic lattice? Like, what are the steps? So there are a couple of steps. First is you're going to atomize them. You're going to break the bonds that they have. Now you can do that in one step, or you can do that in multiple steps. So for example, the first thing I'm going to try and do is I'm going to atomize the aluminum atom. O2, I'm going to keep it as it is. And it's not balanced. So let me just, 1 second, let me balance it first. There's 2Al and there's 3/2 O2. Okay, so now it's balanced. So I'm just breaking it down. So first thing is, I've got aluminum solid, I've atomized it. So that's enthalpy change of atomization. Because if I want to make a lattice, I would have to first break the previous bonds that exist between elements. I haven't touched the O2 molecule yet. So this is CO2 gas as it is. Next step, I'm going to atomize. So the next step is I'm going to atomize oxygen. The aluminium is already done. Aluminium is already a gas. It's split into atoms, and there would be two of them. So the enthalpy of atomization of aluminium will be multiplied by 2. Now I'm going to break down the O2 gas molecules. I'm going to break their bonds and it's going to form 3 oxygen gaseous atoms. So basically this is enthalpy change of atomization of oxygen times 3, which is because you're forming 3 gaseous atoms, or which can also be written as the bond energy 1.5 times the bond energy of O2. Is this part clear?
Yep.
So this was endo. You're breaking the element into atoms. Again, you're doing the same thing. You're breaking the oxygen into atoms. So that's also endo. That's breaking bonds. Now the next step is you're going to ionize. So what you're going to do is, what you're going to do when you're going to try and ionize this is that aluminium has to be ionized. As I said, so aluminium needs to be ionized. So we're going to turn this aluminium into 2Al3 plus gaseous ions. So basically, it has lost how many electrons? It's lost 6 electrons. The oxygen stays as it is. 3 oxygens, gaseous. So how many ionization energies is this? This is the first plus second plus third ionization energy of Al. And that too getting multiplied by 2. Why? Because you got 2 Als, right? Is this clear?
I don't understand the equation.
No, which one?
2Al3 plus 6E plus 3O.
See, I had Al, right? I mean, basically what I'm trying to do is I've got the elements, I'm trying to make the ionic lattice, right?
Yep.
So what do I need to do with aluminium? I would have to first break the metallic bonds of aluminium. So I did that. So that's an aluminium gaseous atom. What do I do next? I turn it into an ion. Once I've broken the metallic bonds, I force it to lose electrons. So that's the first plus second plus third ionization energy of aluminium, right? And that's times 2 because there are 2 aluminiums, right? So if aluminium loses 3 electrons, so in total it's going to lose 6 electrons if there are 2 aluminiums. Is that clear?
Yep, that makes sense.
And I'm trying to do the same with oxygen because over here it's oxygen minus 2 in the ionic lattice, right? So I start off with an oxygen molecule. I break it into its atoms. So I basically break the bonds, like 1.5 bond energy of oxygen, double bond oxygen. Now I need to ionize the oxygen atom as well. So the next step is I'm going to try and ionize that. So how do we go about doing that? It's so that is going to be exothermic. 1 second. So this one, we're going to go down now. Okay, so now the two Al3 plus gaseous, the oxygens are going to consume the electron, so it's going to become 3O minus 2 gaseous ion, right? And that's about it. So what is that? That's the electron affinity of oxygen and the electron affinity of oxygen minus 1. Oxygen is basically trying to gain 2 electrons. And that's multiplied by 3 because you got 3 oxygens doing that. Is this clear?
Why did you sort of do the arrows that way?
So
I didn't understand.
that's because electron affinity is exothermic. I mean, at least the first one is exothermic. I mean, endo is going
Oh,
up.
okay, so now it's going the opposite way. Okay, that makes sense.
Okay, so it's okay. As anyways, so now it's going downwards, right? And we can actually check whether it's exothermic or not because electron affinities can be. I mean, the first one I told you about electron affinity. The first one is always exo. The rest are all endo. So if I look at electron, I mean, this data would be given to you. So the electron affinity of oxygen is 141 in 1 second. It's given in electron volts just. So we'll later on do a question where the actual values would be given. So finally, I'm at this point. I'm at the gaseous ion point, right? Now, those gaseous ions can get together to form this ionic lattice. And that's basically lattice energy. So the final thing that we're going to do is, the final thing that we are going to do is we're going to complete the Hess cycle. And that's my lattice energy. So one path is equal to the other path. So you could make any two paths equivalent and you'll be able to solve this. The simplified, this one looks kind of complicated. I'll try and draw a simplified version as well. I mean, just because of going upwards and downwards, right? The simplified version is for the same. So the simplified version is I got aluminium, solid elements forming aluminium oxide. And there are 3 by 2 O2 and 2Al solid. What you need to do is you need to first atomize. So you need to turn them into 2 aluminum ions, sorry, gaseous atoms, and 3 oxygen gaseous atoms. Once you do that, what do you do next? You ionize. You turn them into 2 aluminum plus 3 and 3 oxygen minus 2 gaseous ions. And once you've done that, this is your lattice energy. And this one over here is your enthalpy change off. formation, and you can have one path being equal to the other path, so it's basically this path versus this entire path. Is this clear? I mean, the simplified version, is this clear?
Yep.
So that's your lattice energy, but I mean, usually they go along with this energy axis. So you start off with enthalpy of formation, which is exothermic. You atomize it, aluminium gaseous, oxygen gaseous. You start ionizing it, ionization energies for aluminium and electron affinities for oxygen. And then once you've got gaseous ions, you join them and you form the lattice, right? So that's the whole process. ठीक है, clear?
Yeah, I understand it, but like, how would it actually be in a
In a
question?
question,
So
I mean, it's going to be
yeah,
exactly the same way. It's you'll be given values. One second, let me just open a question first. We can just a second. So this one. So I'll do one question now. And yeah, this one. So what they're saying is they've given us some data. And what they're saying is that relevant data from the data booklet to calculate the lattice energy for potassium oxide. So we have to calculate, and just hold on a second. So we got to calculate the lattice energy of potassium oxide, right? So I can either make the whole energy axis thing, or you can just go with enthalpy of formation, which is what potassium element, oxygen element, and they're forming what potassium oxide, right? This has to be a solid, 1 mole. This is going to be half O2, right? And this is going to be 2 potassiums. Potassium is a solid, metal, oxygen is a gas, right? So this is my enthalpy change of formation. Whether is this clear?
yep.
And this value is given, that's minus 361. Now I'm going to start making, I'm going to atomize, ionize, and then form the lattice, right? So what we can do is we can quickly atomize it in one step. Like I want to turn the potassiums into potassium gaseous atoms, and I want to turn the oxygen into oxygen gaseous atoms. So what do I need to do for this? The atomization of potassium is already given, that's plus 89. So that's for 1 mole. So this is going to be plus 89 times 2, right? Is that clear? And for oxygen, I need to turn it into gaseous atom. For this, I can use bond energy of oxygen, which is in the data booklet that's given as 496. So it's going to be divided by 2 because I'm breaking half moles of oxygen, right? Is this clear?
Yep.
The next step is I'm going to ionize them. I'm going to ionize them together. So potassium +1, gaseous ion. And I've got oxygen, which is -2, which is gaseous ion as well. So what do I need to do for this? So remember, in this case, just hold on a second. So in this case, remember, I'm actually ignoring all the tiny little steps. I'm just doing the big thing. So potassium into potassium +1, where do I find this? That's the first ionization energy of potassium, the first ionization energy. Usually it's given in the question, right? I mean, these ones are Cambridge questions. The data booklet is given separately. So ionization energy of potassium, that's given over here somewhere. It's 418. That's the first ionization energy of potassium, but times 2 because you got 2 potassiums. Then it's the electron affinity of oxygen because it's turning into -2. So it's not just the first one, but the second one as well. So it's -141 plus the other one as well, which is 798. Right? The oxygen atom first gains electrons, then it becomes -1, then the -1 oxygen ion gains electrons, right? Is this clear? This part?
Yep.
Finally, AQA, the gaseous ions, they form the lattice, so that's your lattice energy. And you just have to solve for lattice energy. How do you solve for this? One path is equal to the other. So that means -361 is basically equal to all of this other stuff, which is what, 89 times 2? 496 divided by 2. It's minus 141 plus 798 plus 418 times 2 plus lattice energy. So you just have to make lattice energy the subject of the equation and you'll be able to solve this. Is this clear?
Yep.
So that's how this is going to be solved. So try making try making the more complicated one, like the one that's shown over here. You could try doing both, but even this one is simple. Like if you get the simpler one, it's just atomize it in steps, turn aluminum into an atom, turn oxygen into an atom, turn aluminum into an ion, then turn the oxygen into the ion as well. Once you got ions, you form the lattice, right? So it's kind of the same thing. So try making so the question is just draw the Born-Haber cycle. Number one, do it for MgO. So do it for calcium chloride. That's it. Draw 2 Born-Haber cycles. One for MgO, one for calcium chloride. ठीक है वर्दा?
Okay.
So just try and do this one, ठीक है? So we'll इसके ऊपर questions नहीं है? Do you have any questions about this?
No, I think I understand it.
ठीक है, so we'll practice more questions tomorrow then, ठीक है? So I'll send
Okay.
you, try and attempt these two. ठीक है?
Okay, I'll try.
चलो, okay then, take care.
Okay.